Hey all, it's Mr. Byros going to make a video about the solutions to the review questions and the assignments we had for chapters 5 and 6, which were forces and energy. So we're going to look at the two problems that we did, and I'll go through a little bit of how we solved them and how we do them. So the first one was for forces, and it said the question concerns the motion of a crate being pulled across a horizontal floor by a rope. In the diagram below, the mass is m. The coefficient of kinetic friction between the crate and the floor is m. I think that's supposed to be mu. We'll just keep moving. The tension is Ft. So there's a rope at an angle that's pulling this box or this crate across the floor. Now there's a few parts here. We need to draw and label all the forces acting on the crate, compute the normal force in terms of m, Ft, theta, and g, and then compute the acceleration of the crate in terms of m, Ft, theta, mu, which should be the coefficient of kinetic friction, mu, and g. So we're going to be doing this in terms of variables rather than with numbers, which is a common thing on the AP test, and we should get used to it. So I'm going to go ahead and switch over to the solution so we can look at that. All right, for the first one, the forces acting on the crate are tension in the rope, the weight of the block, normal force, and friction. So we've got gravity downwards, normal force upwards. Now they've drawn gravity, or FW, this would be force of weight, which weight is gravity, and they've drawn it bigger than the normal force. And that is the case because we have a component of tension that is upwards. Part of this, FTY, is upwards. Now the AP does a weird thing where on their free body diagrams, they will draw these forces at an angle. They'll still expect that if you're solving through and pulling out the components FTY and FTX, they'd want you to do a separate free body diagram to get those two components, the horizontal and vertical component of this. But for some reason, they also like to have the angled forces on there. So we've got our Ft at an angle, normal force up, gravity down, which is bigger than the normal force because of that additional upwards force from tension. And then friction is going to be pulling back to the right, just opposing tension. But you'll notice that friction is probably going to be, or it should be, smaller than the force of tension horizontally because we are pulling and moving the box across the floor. So the vertical components should all cancel out because the box presumably is not lifting off the ground. And the force to the right of tension in the x direction should be bigger than the force of friction pulling back to the left because our box is moving. So that's what the free body diagram should look like there. Now for B, which again asks us to compute the normal force in terms of the other variables. So they are going to go ahead and break this into FTY and FTX with the cosine and the sine, just like we've always done. And then the net vertical force needs to be 0 because we're not accelerating up and down. The crate is only moving horizontally. So if that sum of forces, or the net vertical force, is 0, we get normal force plus tension upwards is equal to the force of gravity downwards. So Fn equals force of gravity, or force of weight, minus this y component of tension, which is Ft sine theta. And we know that the force of gravity, or the weight, is just mg, the mass of the object, times the acceleration of gravity. So lastly here, we substitute that in and get the force normal, or the normal force, is equal to mg minus Ft sine theta. So that is our answer for B. And then lastly, it says that from part B, we notice that the net horizontal force is going to be, just like we saw over here, we have this Ft cosine theta, the x component of tension, and then friction is pulling back to the left. So the sum of horizontal forces, or the net horizontal force, using Newton's second law, is Ft cosine theta minus the force of friction. So this is our force that's pulling to the right with tension. This is the resisting force from friction pulling back to the left. And we can substitute in for friction because we know that is just mu times the normal force. And we have this, from part B, we have this description of normal force, which is mg minus Ft sine theta. We pulled that right from our answer to the previous question. So the horizontal component of tension is pulling to the right, and then we subtract off the opposing force of friction, which is mu times this whole thing, which is the normal force. And then to use Newton's second law, because we're trying to find the acceleration, all we have to do is F equals ma, rearrange that a little bit, a equals F over m. So we take the m from over here and divide. And then this net force is this big thing up here, horizontal tension force minus the force of friction. So we put all that in on the top, divided by m, and that is our answer for part C. We have written the acceleration of the block using Newton's second law in terms of the forces and the mass and gravity and all the things that we have there. All right, so that is our forces. Now, chapter 6 is energy. And for this chapter, the question asks, a box of mass m is released from rest at point A on the top of a long frictionless slide. Point A is at height h above the level of points B and C. The slide is frictionless, but the horizontal surface from B to C is not. The coefficient of kinetic friction is mu, k, horizontal distance is x. So there's our picture. So we slide down from A to B on this frictionless slide, then there is friction between B and C. There's our mu k, coefficient of friction, x the horizontal distance, and h the height. We need to find the speed of the box when it's halfway above point B at 1/2 h, the speed of the box when it's all the way at point B. Determine the value of mu k, so the box comes to rest at point C. Then assume that B and C are not on the same horizontal level, but we're going to have like a ramp. So instead of going horizontally, it's going to ramp up from B to C like so, and C will end up being higher than B, a vertical height y above B. And lastly, if the slide were not frictionless, determine the work done by friction as the box moved from point A to point B if the speed as it reached point B ends up being half what we originally had. So that question just says if there was friction here, and because of friction, by the time it gets to point B, it's going half as fast as it would have been if there was no friction, and then figure out the work done by friction. So we'll take it one at a time, and we'll go through the solutions and have a look at this. All right, so for step 1, we want to find the speed of the box when it's halfway above point B. So what we have is, at the beginning, I'm going to switch up here. At the beginning at point A, we've got gravitational potential energy up here because our object is some height h above the ground, which we're pretty much taking this ground to be our horizontal zero line for the whole problem. And it has GPE but no kinetic energy because it's released from rest at A. At the point halfway between A and B, at 1/2 h, it's got some gravitational potential energy because it's still halfway up at a position of 1/2 h, and it's got some kinetic energy because it is moving when it's halfway down. So looking at that and doing conservation of energy, there is no kinetic energy at the beginning, and then there is potential energy, that's our GPE. So mgh, the full height all the way up there at A, and then halfway down we have kinetic energy, which is 1/2 mv squared, and we also have GPE, which is at that height, which is 1/2 of h, it's going to be mg 1/2 h instead of mgh. So this is the equation that will let us figure out what the velocity is in terms of the other variables. And it's really nice here that all the masses will cancel out. It's the same mass. It's the mass of the object the whole way through. So those m's are going to cancel out, and we just get gh, and we can subtract off. We've got mgh here, 1/2 mgh here. We can subtract this 1/2 mgh from this side over here, and we're just left with 1/2 mgh on the left side. And again, the m's cancel out, the 1/2s cancel out, and our velocity is just the square root of gh. So once you go through and do the algebra for that one, after setting up conservation of energy, we see that with no initial kinetic energy and gravitational potential energy based off h, and then once we're halfway down, we have kinetic energy, 1/2 mv squared, and we are basing our GPE off of a height of 1/2 h. So the thing that changes here is GPE is h there, 1/2 h there. All right, so for the question B, now this is asking us when it gets all the way down. Now we're looking conservation of energy between point A and point B. So when it gets all the way down there, applying conservation of energy again, now we've still got zero kinetic energy at the beginning. we still have mgh all the way up at the top, and our velocity at b, which they're calling vb, is just this kinetic energy is based off 1/2 mv squared. That's our equation. And once we get all the way down to b on the horizontal zero line, we have no gravitational potential energy left. So now we have mgh equals 1/2 mvb squared. The m's are going to cancel out again, and ends up looking very close to the same thing. However, we've got this 1/2 that's not going to cancel out, so we're going to have to cancel out the m's, multiply by 2, and then take the square root to get our velocity vb, which ends up being the square root of 2gh. So these two are two different velocities. This is going to be a smaller velocity when you're halfway down. This will be a bigger velocity when you've reached the bottom at b. All right, the third question. So again, part C. Determine the value of mu k so our box comes to rest at point C. So now we're looking at, as it slides across this surface with friction, the work done by friction causes the box to completely stop by the time it gets to C. In terms of energy, we know that that is our thermal energy, and they're going to write it a little differently than we have. So they're writing the work energy theorem. We know that the work is equal to the change in kinetic energy. So the velocity at C is 0. It's come to a complete stop. The velocity at B, we know we have that from up here. So they're doing, rather than doing conservation of energy, they're just saying the work done by friction shows us that the change in kinetic energy is equal to 1/2 m times the final velocity squared minus the initial velocity squared. If you write that out and expand that, it would be 1/2 m times vc squared minus 1/2 m times vb squared. Those would be your two kinetic energies. Kinetic energy at the end at C minus kinetic energy at the beginning at B. So this is a good way to do it if you want to use this work energy theorem. Alternatively, you could just set it up and say the thermal energy, when it's all thermal at C, is equal to the GPE at A, and that is just mgh equal to the work done by friction. And you could do the work done by friction based off of mu k, the normal force, and the horizontal distance x. All right, so going back to this, we know that the work done by friction is equal to, and this VC is 0, so we know that it's just negative 1/2 mvb squared. And when we substitute in our answer from part B, this was our answer for the velocity at point B, and we stick it in here. That's our square root of 2gh. It gets squared, so the g and h will no longer be square rooted. The 1/2 will cancel with the 2, and it comes out pretty nicely to be negative mgh. So that's the work done by friction. So if that work done by friction is negative mgh, we know that that work is the force times the displacement times the cosine of the angle between them. Now what they're doing here, you'll notice a negative sign. What they're doing is they're accounting for the fact that if friction is acting to the left and the object is moving to the right, technically that's a 180-degree angle. The way that we had set up our problems before, we already accounted for that, so we didn't have to worry about any negative signs from our cosine theta in the work equation. But here in their work equation, they're just accounting for their cosine theta ends up being a cosine of 180, so they put a negative sign in. So they'll still get the right answer, just like we have. It's just a slightly different approach. Okay, so negative force of friction times x is equal to negative mgh. And what they've put in for force of friction is this mu k times mg. What they're doing there is the force of friction is the normal force times mu k, and the normal force in this case, as it's sliding across this horizontal friction surface, is just mg, because normal force is equal and opposite to gravity. Gravity's pushing down as it slides across here, normal force pushing back up, equal and opposite. So, where were we here? There we go. There's our mu k times mg, which is coefficient of friction times the normal force. So they just solve for mu k, the negative signs cancel out, mg's cancel out, it ends up looking really nice. Mu k is just h over x. The coefficient of friction would be the height divided by that horizontal sliding distance in order for the object to completely stop at point C. All right, now for a ramp, which is our next part, if we're considering that point C is higher up, so instead of sliding horizontally with friction, we're sliding up a ramp with friction. So we're going to look at conservation of energy. Now they've set it up to say that the kinetic energy at the beginning, so at B, this is our kinetic energy, 1/2 m times VB squared. That's from all the way over here. Said that 1/2 m times VB squared, that's our answer for the velocity at point B, which we got from part B. So again, we have to go all the way back to part B and say our kinetic energy at point B is equal to 1/2 m times the velocity at B squared. There's no GPE at the beginning because point B is just on the ground, so our GPE is 0. Now here's where they're putting in the work of friction. So what we've done is we've taken this work of friction and just put it over here as the thermal energy. You can really do either one. You can either put it on the right side and say that this thermal energy shows up at the end, or you can put it over here and say it's the work done by friction. The reason that they're on opposite sides is, again, that thermal energy is going to be a positive amount of energy, so it's going to be over here. This will be a negative number because of that cosine of 180 that I mentioned earlier. So either way works. I prefer to do thermal energy over on the right side, but they're just doing the work of friction. So we have the same thing from before. Work of friction is the force of friction times. Now we have to be a little careful because we're not going a distance x anymore. Our displacement is no longer this horizontal x. Our displacement is now L. We're going up the ramp all the way from B to C. So that's the displacement. Work is force times displacement, and the negative sign. Yeah, so we'll figure out how they. Okay, there they go. There's their cosine. And then at the end, it's completely stopped, so there's no kinetic energy at C. There is potential energy. There's gravitational potential. The reason for that is that C is now some height above B, so we've got our height y, and our gravitational potential energy at C is mgy. So that's everything there for conservation of energy. Now we're just going to substitute in a little bit here. So mg times h minus y, that's when we take this from over here and subtract it from this. So they're combining the two GPEs to get this. And then they're expanding on that force of friction. It's mu k times mg. And this cosine theta, just to clarify, this is not from the work. This is not the work cosine theta. This is to show that the normal force on a ramp, which we looked at briefly, the gravity is acting straight downwards, but normal force is not acting straight upwards against gravity. Normal force is acting perpendicular to the surface of the ramp. So the normal force is acting at a right angle to L, so normal force is acting up like this, and it's not exactly the same direction as gravity. So because of that, we have to be a little careful and note that the change in angle here is going to affect our normal force, so that's what this cosine theta is. Now in class, I think at one point we went through and did a whole long process. The easiest way to remember this, rather than doing it every time, is that normal force on a ramp, when your theta is down here, normal force is going to be mg cosine theta. So normally, the normal force is just opposite to gravity. Here it's mg times the cosine of theta, because the normal force is going to be balancing out only a part of gravity, not the entire force of gravity. And that part of gravity is mg cosine theta. So again, we do the math, we work it through, we have our cosine. The mg's are going to very nicely cancel out again, and mu k in this case is h minus y over L cosine theta, and they're just noticing that L cosine theta is this hypotenuse times cosine theta gives you this adjacent side x. So they're simplifying it a little bit. All right, last but not least, we have, if the slide were not frictionless, determine the work done by friction as it moved from point A to point B. If the speed were half what were calculated in part B. All right, so here, what we're looking at is same thing at A, there's no kinetic energy, we have GPE. And then now we're adding in friction. So here's our friction showing up. So when we take that velocity at B, when it gets all the way down to B, and say that we now have half the amount of velocity, because when it is sliding down from A to B, now we're saying there's friction all along this slide. So when it gets to point B, originally we had a velocity from part B, we had a velocity of square root of 2gh, but now we've got half that much. So we've got friction, we've got half the velocity, it's slowed down because of friction on the initial ramp, or the initial slide. So we got 1/2 VB, 1/2 square root of 2gh, and really we're just saying here's our GPE at A, here's the work of friction, here is our kinetic energy when we get to the bottom at B. And at B there is no GPE, it's on the ground. So we go ahead and put that in, it's just 1/2 times squared, so make sure you square the 1/2 as well, everything inside the parentheses. This ends up being 1/4 mgh, and this works out really nicely. We've got mgh here, so the work of friction, or the thermal energy, again, we could put this over here as thermal energy because that's the type of energy that we'll get when we have friction on the slide, but they're just asking for it in terms of work of friction. So the work done by friction, if we take the mgh subtracted over from this side on the right, we get -3/4 mgh. That's 1/4 minus 1 mgh. So the work of friction, we should get -3/4 mgh in terms of the other variables. All right. Well, that's kind of a lot, but that's how we walk through those problems and do them, both the forces problem and the energy. So we're looking at forces, free body diagrams, making sure we use Newton's second law for acceleration, and our types of energy, gravitational potential, kinetic, and thermal energy, the work done by friction showing up in the energy problem. All right, we'll hope to see you all in the Zoom meetings next week, and thank you very much for your time.